Okay, so we have been discussing signs of a chemical change, chemical and physical properties, as well as chemical and physical changes. And I would like to spend a little bit more time on the law of conservation of mass. So, what you're going to need to do is in your Google Classroom, you're going to find an attachment that is identical to the one that I have in front of you, Conservation of Mass Notes. And you're going to open that up and you're going to fill it in with me as I fill it in. Now, keep in mind, you do have to spell things correctly and space it out exactly as I do, or when you check this worksheet, it will mark some of your information wrong because it's going to be computer graded. So this is an assignment that we're going to fill out together. It's notes we're going to take together, but when we're done, you're going to turn it in for a grade. So the law of conservation of mass states that matter can never be created or destroyed. Okay, so the amount of material that we put into a reaction is going to have to equal the amount of material that comes out of a reaction. So the mass of what goes in must equal the mass of what comes out. And there's basically two ways that we can look at this that we're going to discuss more as we go through these notes. But one is we could set a group of reactants on a balance, and we could run a reaction, and we could show that the mass of the reactants are equal to the mass of the products at the end of the reaction. The other thing we can do is something that we've experimented with a little bit, and that's to balance a chemical equation by adjusting the coefficients in front of the molecules, those big numbers, to show that the numbers and types of atoms going in are equal to the numbers and types of atoms coming out. Okay, so if we were showing magnesium and oxygen reacting together to form magnesium oxide, and we had 48.6 grams of magnesium and 32 grams of oxygen, the amount of product we would form, the magnesium oxide, would be equal to adding up the 48.6 and the 32 grams together. So that's going to equal 80.6 grams of magnesium oxide. So all I would have to do is add the two reactants together to get the mass of the product, because what goes in must come out. So a chemical equation is what we write to represent a chemical reaction. And I have one written below, and I do apologize, my worksheet's a little bit messed up here, and the arrow is going through one of my products. But a chemical equation represents really what's going on in an experiment. So in this drawing of an experiment, we're showing the reactants, this calcium chloride and sodium sulfate, reacting together to form a new product. And the numbers and types of atoms going in equals the numbers and types of atoms coming out, along with proving that the mass before is equal to the mass after. So when a chemical equation is written like this, to represent a chemical reaction like this, the chemicals on the left are known as the reactants, and the chemicals on the right are known as the products. Okay? So the diagram below shows a chemical reaction between calcium chloride and sodium sulfate. The reactants in this reaction include, and this might be a little bit tough for you to type out, and I will not put the little subscripts as subscripts, I'll just write them as regular numbers. So CaCl2 space plus space Na2SO4. These are our reactants. And then our products are what's on the right. So on the right, we have being formed CaSO4 space plus NaCl. And again, I do want you to notice that the types and numbers of atoms going in are equal to the types and numbers of atoms coming out. Now, this equation has not been, oh no, it has been balanced. I take that back. It's balanced up here. So really, I didn't write the 2 in front of this, but if I did, that would show it was balanced. Okay, so notice that the starting mass on the balance of the calcium chloride in the test tube and the sodium sulfate in the Erlenmeyer flask is 323 hundredths of a gram. When the test tube is inverted or tipped upside down and the two chemicals mix, the products mass out at that same number, 300.23 grams. Okay, below is a physical change of salt dissolving in water. Look at the mass of the salt and the water on the balance before the dissolving takes place. It's 180 grams. What would be the weight of the salt and water mixture on the right when we dump the salt into the water and let it dissolve? Okay, because of the conservation of mass, we know that during the course of this physical change, the mass is not going to change, although the product looks different because the salt is now dissolved. The mass is still going to be equal to 180 grams. Okay, sometimes matter can look like it has been destroyed, and I emphasize look like, but it is actually not. This has to do with gases that are formed during a chemical reaction and escape. So if a gas is formed, it can sometimes escape and make it look like the products actually weigh less than the reactants. So it's important to run chemical reactions in what we call a closed system where everything is sealed and all of the products, including gases, are trapped. When reactions are run in an open system, the products of a chemical reaction like gases can escape, and it can make it look like the reaction is actually losing mass, but really when the gases escape, those gases are made up of atoms that weigh something. And if we could trap those gases, we could show that the before and after mass are equal to each other. So I have a diagram down here to illustrate gases being formed and escaping in an open system where we don't have a cork. And then over here, if any gases are formed, they're going to be trapped in our closed system. So below is a chemical change of magnesium reacting with hydrochloric acid to produce hydrogen gas. What would be the weight of the products on the right after the chemical reaction ends? Now notice bubbles are going to be made because there is a reaction taking place, and that's the sign of the chemical change. So that means a gas is being formed, but also notice we have an open system. So as those gases escape, it's going to look like we lost mass. So actually in this reaction, the products will be less than 180 grams. Less than 180 grams, not because we actually lost mass, but because the gases escaped in an open system. If we know the mass of either the reactants or the products, we can determine an unknown mass because matter is never created or destroyed. Okay, we can use the law of conservation of mass to find out the missing information. So if we take 3.4 grams of hydrogen gas and we react that with 10 grams of oxygen gas, then we will form, and notice that I did not balance this by putting coefficients, but what we will have formed when we add those two together is 13.4 grams of water. Now, when you fill this in, make sure you don't put a space between the 4 and the G. Okay, when methane gas and oxygen react to form carbon dioxide gas and water, okay, 12.2 plus 14 is 26.2 grams, okay? And so you're going to notice that 20 grams of water is produced on the right, which means if we form 26.2 over here, the missing amount would be 6.2 grams, okay? So that's what we're missing on the left there. All right. And then when we go to mercury oxide decomposing to form mercury and oxygen gas, we can see that we started with 23.6 grams, okay? and the oxygen gas is 13 grams. So if we subtract those two, all right, we're going to see that mercury, the gas that we have left over there, is going to be 10.6 grams. When we add those together, it'll equal to 23.6. So when we're dealing with missing information, it makes it very easy to find what's missing, because we know that in chemical reactions, mass is always conserved. And what goes in must equal what comes out, whether it be the mass of the reactants in the products or balancing the equations and looking at the numbers of atoms. So when understanding the law of conservation of mass, we can look at two different things: the mass of the reactants going into the chemical reaction and the mass of the products that come out of that same chemical reaction, as shown in this chart above. So what we're going to fill in here to prove the conservation of mass, we could run the reaction on a balance, okay? And the other thing we could do to prove the conservation of mass is we could look at the numbers of atoms going into a chemical reaction and the number of atoms that come out of that same chemical reaction. So we could count atoms and balance the equation. Okay, and again, in order to get this right on your worksheet, you have to type it in just as I typed it in. But both of these things will prove your conservation of mass, okay? The number of atoms that goes in to a reaction must equal the number of atoms that come out. Below is a chemical reaction or a chemical equation to represent a reaction that takes place between magnesium and oxygen. So how many magnesium atoms are going in? Okay, this means 2 magnesium atoms. How many are coming out? This little number next to the Mg, if there's nothing there, it means 1. So 2 times 1 is 2 coming out. Then if we look at oxygen, we have 2 oxygens going in. Now this 2MgO means we've got magnesium oxide. So we have that molecule twice. So 2 times 1 is 2 oxygens. So is the above reaction or equation balanced? Does it obey conservation of mass? Yes, it does. So this is just a quick little refresher if you're confused about counting atoms. Remember that the subscript is the tiny number written at the lower right behind the chemical symbol. So this little number right here, and if there isn't one, like behind the carbon and the calcium, it just means 1. It tells you the number of atoms per molecule. So this is 1 molecule of calcium carbonate, okay? And that molecule has, there's no number after the calcium, so 1 atom of calcium, no number after the carbon, so 1 atom of carbon, and a 3 after the oxygen, so 3 atoms of oxygen. Our next molecule is a water molecule. We have 1 water molecule, and that molecule has 2 atoms of hydrogen, and there's no number after the oxygen, so 1 oxygen atom in that 1 molecule of water. And then this is a molecule of sugar, table sugar or sucrose, and this molecule has 12 atoms of carbon or 22 atoms of hydrogen and 11 atoms of oxygen. Okay, the subscripts tell the ratio of atoms in a molecule and can never, ever be changed. If you change the subscripts, those tiny little numbers, you'll actually change the chemical, okay? So water is H2O, okay? And hydrogen peroxide, peroxide is H2O2. So you can see if I needed 2 oxygens, I could not put a little 2 after the oxygen in water because I would change the chemical. H2O is water, H2O2 is hydrogen peroxide. Okay, the coefficient then is the large number in front of the chemical symbol, and this indicates the number of molecules. So for example, this big number 4 means I have H2O, 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 H2O. I have 4 molecules of water. So 4H2O means 4 molecules of water. So when we get a total, we multiply the number of molecules by the number of atoms per molecule. So we'd have a total of 4 times 2 is 8 hydrogen atoms. 4 times 1 is 4 oxygen atoms in 4 molecules. In 4 molecules of water. Now, H2SO4 is sulfuric acid, and 3H2SO4 means that we have 3 molecules of sulfuric acid, for a total of 3 times 2 is 6 hydrogen atoms. 3 times no number after sulfur, 1 is 3 sulfur atoms, and 3 times 4 is 12 oxygen atoms. So hopefully that refresher will help you in trying to balance chemical equations. So just wrapping it up, remember that what we're discussing is conservation of mass. There's 2 ways that we can show that mass has been conserved. We can run a reaction on a balance and show that the mass or the weight of the reactants is equal to the mass or weight of the products. The other thing we can do is balance a chemical equation and show that the number of atoms going in is equal to the number of atoms that are coming out of that reaction.